All right, so I'm going to give you the two questions, that extra questions that I played around with, and you can prove them if you want. Maybe I should give them as homework assignments. This could be your homework assignment, actually. Yeah, I proved them. You should prove them too.
I proved the Riemann hypothesis.
Yeah. I've constructed the real numbers.
I've already won my $1 million. I expect you to as well.
So that's the first thing I had to clear out of my mind. So I'll give it, it's not that hard to prove this one. And the second one is if X and Y are the Euclidean topology, I gave this last one to Chaos and Fractals last semester. So here it comes again. So I'll type these up. These can be your homeworks. This now is easy to prove using the basis elements. So last semester, we didn't have a basis, like that was not part of Chaos and Fractals. In fact, I don't think he even defined topology. Don't think we had that. Maybe I did.
You might have, I don't think you gave us.
Yeah, but it probably seemed like way, like what? So now this, like you can use that theorem to show F inverse has to be continuous under those conditions with the Euclidean topology, because your basis elements are open sets or open intervals. So what I would recommend doing for number 2 is start out with just one open interval and show that F maps that one open interval to an open interval if F is continuous. And that's how to do the homework.
Like we probably talked about.
It was hard because I was pulling things from the book and then I realized, oh, he's using this. But the forward had that the book requires no background knowledge whatsoever. Except what? He used to come here. So Devaney used to come here every year and talk to MA 103. I don't know. When I was here the first time he came. And
Wait, was that when you would show the video? That's like a core memory of my dad's experience.
What?
It's just like being down what's the
Julia sets and the fractals.
Yeah.
And the Mandelbrot sets.
Yeah.
And then
Showing the zooming in of the Mandelbrot set.
It's just yeah, more like such like you know, and then they that. So
Yeah. All my son remembers everyone.
yeah.
Yeah, I was so excited when he came because, you know, that was the field I was in. And I remember asking the cadets, like, didn't you think that was cool? Oh, I don't want to give this as an in-class assignment. And they said, ma'am, he seemed a bit excited by his bulbs. Like, okay, they didn't think it was cool. All right, I'm going to show you one more example just in memory of chaos and fractal. You learn a lot in that class. So S1, we'll start using this notation for circles and spheres. The unit circle in R2, it's defined as the set of coordinates such that x squared plus y squared is equal to 1. So we're down to pre-calc again. So your whole space, and I'm going to put the usual topology on X. And yeah, so both of them are, and Y is also equipped with both of them. So we worked a lot with this in chaos and fractals because you can actually define maps on the unit circle that are pretty easy, like f of theta equals 2 theta, and it's chaotic. So one of the really cool things is that there are orbits or trajectories we can take that will be dense on the unit circle. Start up. So if you just think of pushing a button over and over, and you take f of theta equals 2 theta, so it just doubles the angles on the unit circle. What'll happen is you'll get if you start out with an irrational initial condition and you just push that button again and again and again, it'll eventually cover the entire circle. It's dense. So he defines f of theta on these two spaces. As being theta, p sub theta, where p sub theta is the point. So the reason, the reason we don't, we actually used maps like the one I just showed you up here is because we don't really need to specify two values. If I have theta equals pi over 4, I already know what the x and y coordinates are that correspond to pi over 4. So instead of having two coordinates, I really have to worry about theta, the angle. So if you think of the angle going around that circle, any point on that circle is defined by an angle. And so you can take a map from the first space, which is 0 to 2 pi, with the 2 pi not included. And then for each of those angles, I know where I am on the unit circle. So we are back at pre-calc. I think Colonel Craig is teaching MA 100 right down the hall. He's probably teaching the same things. So it turns out that F is a bijection. And F is continuous. Thank you. Now I don't have to prove it. And it's actually kind of easy to see why. If I take any open interval on the unit circle, I can string it back to an open interval on 0 to 2 pi. However, if I take an open interval on 0 to 2 pi, I can just make it fold over the 2 pi on the other side, so that partially some of it is on one side of the circle and partially some of it is on the other side of the circle. And so that's why F inverse is not continuous. I'll show you that. You can show F as continuous on your own. It's not obvious. You have to take a basis element from one side. And remember that if you have 0 inside your element, it's closed because it's open because my X it's the same as you would have, yeah, so you take this, if I have a unit circle like this, so I just go like this, take it and put the usual topology on it. So, if I take I'll show you the picture I have. And he has this in the book, so I just like literally went in the book. So after I did all those questions with, let me come up with an example, does it work for finite sets? Does it work? Finally, I read the next page and he has a counter on the next page. But I feel like this one's contrived because what he's doing is going across the circle and he's just mapping something so it splits across that circle. So it seems kind of like a fake example where my finite complement topology was, you could really see like, hey, if I go back and forth, it doesn't work. So let me show you with pictures what's going on.
The reason you're keeping closed bracket, open bracket for all the bottom sets is because we're starting with
0.
0.
Right. It's like 0 is like minus infinity.
That's what we should, is because we're going back to X.
Right.
0, 2 by number.
So here's a picture you should think about on S1. Any closed curve is really a circle. So all my curve, like now I can draw things and tell you it's a circle. There's my S1. So the way he's coming up with this counterexample is just having it split over the point. Because 0 and 0 and 2 pi is 2 pi is not included, right? So if I just have something hovering 0, I'm going to be up on that side. So you have it pooched over the 2 pieces. And that's how he creates the counterexample.
So it's satisfies the 0 amount.
Yep. Exactly.
What's the E?
Oh, I just made up 2 points. So like if I have 0 to E union G to 2 pi like that. Right. So that's that part. That's that part. All right, I do want to show you some cool stuff. I really like complex analysis, and a lot of what I'm showing you right now, it has to do in complex analysis, you have to use topology because you're shrinking things, you're doing manipulations on the complex plane. But we're going to look at it in R2.
Just transplant all of them.
Even trick people into taking a really hard class.
We'll let you know how we're gonna figure it.
It's like, I just can't believe it.
Yeah.
It's only the eighth or so of figures.
Brought up the sign up sheet and said you're doing the class. I just, I don't know. No effect.
Yeah,
I never
so
really-
that's a yes.
True.
I need to remember how I signed into this class.
I don't remember how you signed up for this class.
There we go.
Yeah.
Was the person who signed you up for this class a math person?
What now?
Was the person who signed you up for this class a math person?
That's great. I literally got sent the schedules for here and I was like, oh, I don't know what any of these are. And then I pulled up in here and I was like, what in the world did they do?
Well, okay.
Make them listen to the videos.
Oh, I'm gonna tell them next year because like a lot of us have put in classes and we don't have the prereqs. It just doesn't make any sense.
Yeah.
I'm gonna tell the people next year, like, please, like, don't do a stereotype. But like, this one's fine because
Okay.
they're like, you're so understanding. But for some of them, it's like, why would you do that?
No, I know like James Beckwood, he's an econ major, and he got put in our like public economics class. And to be fair, like, even a lot of people that took metrics aren't really good at metrics, but he had never taken econometrics, and it was like totally metric based. He'd never used data, so he got like a 50% on the first grit that was like metrics based, and like a 0% on the first empirical exercise if you didn't know how to use data like at all.
Yeah.
And then drop it.
Yeah, they really did not even think over.
Okay, that's my version of R2. It's the plane spread out. That's topologically equivalent to the half plane. And that's topologically equivalent to these three things are the same. And I remember people who had topology or who were topologists always working on the unit inside the unit thing. So it's inside there. So the outside's open. You don't include the boundary. That part inside here is really R2. You really have R2 can be put into an itty bitty living space.
Yeah, what are the squiggly lines about the equals?
Oh, that's topologically equivalent. So we can't say equals. They're not exactly the same, but they're topologically the same. So open sets here can be identified to open sets in here. Squishing something in R2 is the same thing as squishing something in the half plane. Well, the same thing as squishing something inside the disk.
So we benched into the map where it's like there's the same, and then there's basically the same, and then there's basically the same, once you're saying pretty close. All right.
So the functions that do that. Do this.
That is in fact anterior.
All right, this is my last slide, so I'm gonna have to fit in everything in the last slide. The functions that make it do this, I was actually playing around with some of this because like, okay, you can prove things because they're actual functions and you're working with the Euclidean topology. The first function that takes you to the right side of the plane is just keep the y values the same, but let the x values be e to the x. Then if you put in any from minus infinity to positive infinity, you put it here, you'll get the range of all positive, the top half of the plane. And then the y values would just stay the same as whatever you had on r squared. The function that takes you from the half plane to disk is that theta. So you're literally squishing. So let me show you what that looks like. So if I take, here's the unit disk. If I take a point somewhere on the plane, so this is my point on the plane. I actually have numbers here. So I took like the radius was 1. Well, you could take 2. And this is pi over 4. If I take 2 here, the new radius would be r divided by 1 plus r. So that's going to be 2 divided by 1 plus 2, which is 2/3. It's just going to map this thing back down across pi over 4 down somewhere here. So you're literally taking every single point on the plane and moving it down into the unit disk. Which is pretty cool. I indeed have in my notes, it squishes the plane into the open unit disk. So I'm not going to show you today that it's in the book, but the surface of the cube, just the surface of a cube in 3 dimensions is homeomorphic to this unit sphere. And I want to show you the punctured sphere is really the R2, which we did in chaos and fractals. So let me show you what that looks like.
Is the unit sphere just the boundary of the sphere, or is it?
It's the inside of the sphere. So it's the same squishing idea. So you have the surface of the cube, every point on the surface of the cube, it's identified by functions. You can actually literally do, it's 255. You can literally do the calculations and show that every point on top of the surface of the unit cube, or any cube, doesn't matter, gets squished into the sphere, inside the sphere.